Hello everyone. So I'm George. I'm one of the lead developers of Agents.jl. This is a software to create agent-based modeling simulations. Along with Tim Dubois, we gave a workshop on Agents.jl in the Social Simulation Conference 2021. And in the video you're seeing right now is the first part of this workshop. It is an introduction to Agents.jl, how to use it, how to get started, and why you should care about it. Please do keep in mind that this video has at least some basic assumptions about Julia familiarity and agent-based modeling familiarity. So with that being said, please do enjoy. Bye-bye. Cool. All right. So welcome in this session of the workshop. So we will be going through Agents.jl, which is a Julia framework for agent-based modeling. On the screen, you see three simulations that are actually done with Agents.jl. The first one is actually the logo of Agents.jl, which is a simulation of an SIR model, so a virus spreading in a continuous space. The second is an interactive application that showcases the DAISY world simulation, which is done in discrete space. This should be playing, sorry, yeah. And this one is a simulation of a zombie outbreak in an OpenStreetMap. So this should also be playing, apologies. So this is just some fancy animations to make you interested. And now I will give you something, let's say, a bit more rigorous on why you should be considering trying out Agents.jl as your framework for doing agent simulations. And I will give you five central characteristics of Agents.jl. And the first is that it is a futureful library. So of course, it has all standard functionality you would expect. It has 4 different kind of spaces that you could create your agents in. Other things like flexible data collection, multi-agent support, and many other things that, of course, I don't have space to write here. So this is the link to the documentation of Agents.jl that you can find all this stuff. The second, let's say, central property of agents is that it is very, very, very simple, and this is by design. So we have made it to have a harmonious and general API, and to use it, you need to write little amount of lines of code, which means that Agents.jl has a short learning curve. And in fact, it is simpler than Netlog or Mesa, which are other, let's say, famous ABM software. And more details about this can be found in our paper about agents. The third property of agent is that it is fast. It is written purely in Julia, and besides this has also been further optimized to be as fast as at least we could make it. And besides this, it also allows for distributed computing, which is something you will see more in the section 3 of this workshop. And it is in fact faster than Netlog or Mesa, which once again is information you can find in our paper. Agents.jl is also interactive. Of course, as you have already seen, Julia is a dynamic language, so you can interactively check your variables and change your data structures. When Agents has been designed with the same philosophy, but it also has visualizations and interactive applications that you can play with live. And it has an API that is extendable and adaptable to your own simulation setup. And the fifth, let's say, central property that could be even one of the most relevant for you is that it is an integrated piece of software. It integrates with the entire Julia ecosystem. What does this mean? Well, for example, the main output of Agents.jl is a data frame, the data structure you just saw in Bogumel's section. It is also having integrations with, let's say, differential equations, light graphs, optimization techniques. So it really ties nicely with the entire Julia ecosystem, which means that if you do some work with Agents.jl, you can really use this work straightforwardly with the rest of the ecosystem. So to show you how this is, well, I will not show you everything, of course. My part of the tutorial will be to show you how you would make a very simple agent-based model in Agents.jl. And in this tutorial, we will be making the shelling model. Now, what you see in the screen is my empty VS Code editor. So I will be making everything from scratch in this editor. And on the right-hand side, I have the rules of the game, the rules of the shelling model. And this is a very straightforward model, and I'm guessing many of you will know it already. So how does this work? Well, the model says agents live in a 2-dimensional grid with a Chebyshev metric. This is simply a fancy way of saying that there are 8 neighbors around each grid point. So imagine you have a square grid, and around every point there are 8 neighbors. The agents can belong to one of 2 groups, let's say 1 or 2, and they can be happy or unhappy. And each position of the grid can be occupied by at most 1 agent. The model is populated by n agents that are less than the total amount of possible positions in the grid. And of course, half of the agents are from one group and the other half are from the other group. So that's the story. And what I'm going to do now is show you how we're going, oops. Yes, that's exactly it. So wait. Yes, perfect. So how we will create this model is we will be following the tutorial of Agents.jl. So in front of you is the documentation of agents that you can find online. And the tutorial tells you the steps. So it says that in agents, there is some kind of central structure that maps unique IDs, identifiers, to agent instances, just like a dictionary would work. And the simulation progresses in discrete steps. And during one step of the simulation, you, the user, decides which agents will act and how they act and what they will do. So the first step in making this process is to simply decide what kind of space the agents will live in. And there are many options, but in our case, we already know the answer. And the answer is that the agents will live in a discrete space. So to do this in agents, I start by simply using agents, which is the package we will use. And then I think the space I want to need. And in agents, there is this structure called grid space. And the grid space first takes a tuple, that is the dimensions of the grid. And it takes some other arguments as well that we will not need at the moment, because let me type it here. By default, you see that the space has the properties we need. It has by default the Chebyshev metric, and by default is periodic. So this is the kind of space that agents will live in, and that's nice. And this is already step 1 for making your own model, making simply this decision. Now, step 2 is to define the agent type that will populate the model. And to do this, you simply create a standard Julia mutable struct that is a subtype of abstract agent. And this type must contain 2 mandatory fields. The first is the ID, the identifier of the agent, and the other is the position. So how do we do this in Julia? Well, we say, okay, let's create a mutable struct that we call, mutable struct that we call selling. This is how we will call it. And this has to be a subtype of abstract agent. Okay, so this is the subtyping symbol. And we start, and we already know that this must have at least 2 fields. One is the position field, and the other is the ID field. Now, the position, of course, is a tuple of 2 integers, so the X and Y location on the grid. And then, according to our specification, we also have to add whatever other properties the agent will have. And here we already know, okay, the agents will have 2 properties. The first will be the group they belong in, that is just an integer. And the other property will be whether they are happy or unhappy. So I here will just type happy, which is a Boolean. And if the agents are happy, this is obviously true. And if they are not happy, this is not true. And that's the end of the story. And that's already step 2. We are going very fast, and you will see how simple it is to finish these 6 steps. So after we have created the agent type, then we have to put this agent type and the model space and additional optional model level properties in our universal structure that is called agent-based model. So this is just a structure from Agents.jl that puts everything together and allows you to do things. So let's do this. Well, we already have the agent type, that's the agent type, selling, and we already have the space. So here's the space. Now, the other thing we have to do is make one model level property. Which model level property this is? Well, if I scroll down here into the rules of the selling model, it says, okay, at each step of the simulation, each agent does the following. It counts the nearby agents that belong to the same group. And if these are at least meant to be happy, then our agent becomes happy and stays where the agent is. Now, if the agent is unhappy, it moves to a random new location. From this, we deduce that we need a model level property that is called mean to be happy, or however you want to call this. And how it is typically done in agents is you create a new variable called properties. And this variable is a dictionary. It's a dictionary that maps the name of the property, which here is mean to be happy, and it maps it to its value, which for our case, this will be 3 in our example. So these are the 3 arguments I have to give when I am creating an agent-based model. So how do I do this? I simply type model equals agent-based model, and then my first argument to this model would be the agent type. So, okay, let me copy paste it. Selling. The second argument will be the space. Then the optional argument, and this is why I have this semicolon over here, because semicolons mean keyword arguments, which are typically optional arguments, right? And here I will type properties. Okay, notice that properties is a keyword, so I should have wrote, okay, let me put this a bit on the side. So I could write it like this, properties, but because the keyword and the variable name are the same, I don't have to do this. This is not a feature of agents, this is a feature of Julia, so this evaluates perfectly. And it's finished, and actually because model has a nice pretty printing, I have it here in the console. So it says, okay, this is an agent-based model with 0 agents of type selling. It has this space, and it has this scheduler. Now, the scheduler is something I have not talked about, and it simply means according to what order are agents going to be activated when the model evolution starts. And by default, this scheduler is called faster. Actually, you don't have to know this because we will change the scheduler. We actually don't want the faster scheduler. We want a different scheduler that is coming from the scheduler's submodule, and it's called randomly. Okay, so this simply means that agents will be activated at random at each step. So now I will create again the model, but I will also give it the scheduler argument, so that our scheduler is now the random one, or the randomly one. And perfect, that's pretty much it. Now, of course, what we actually have to do is to populate this model with agents, because as you can see, it doesn't have any agents, so it probably won't do anything useful for us. And what I like to do is to create a function that initializes the model and populates it with agents. And this also interplays nicely with Agents.jl API. So we start with a function that we can call it, I don't know, init or initialize. And this function will only take keyword arguments. And n, which would be 320, this will be the number of agents we will put into the model. M, that will be 20. This is simply the amount of grid coordinates along each dimension. So now the grid is 20 by 20. And then we will have the mean to be happy property, that is 3. And that's it, actually. We don't need anything else at the moment. So inside this function, I simply copy paste some stuff over here. So space will be m by m. That's nice. And then scheduler will be schedulers randomly. And then properties will be this nice dictionary. And of course, this will not be 3, but it will be our variable mean to be happy. And then I create the model, which once again, I copy paste it. I hope the font size is large enough, right? If not, someone will tell me, I hope. Also, I cannot see the chat, so if you ask questions, either someone has to convey that to me live.
I'm answering them, Josh. Oh, good.
Perfect. Thanks, Tim. Cool. So inside the function, this is the point where we create the model. And now this is the point where we actually add agents, right? So we will say for n in 1 over n, something, end. So in this loop, we will add n capital N agents to the model. Now, the first step is to create the agent. So agent will be a selling that has identifier n. It is in position 1, 1, and it belongs to which group? Well, here is, I will type something a bit fancy, but don't worry, it's very simple. 1, 2. What this says, this is something that is called the ternary operator. It says, if condition is true, return this, else return this. So this simply means that half the agents will belong to group 1 and the other half will belong to group 2. And as you will notice, every agent starts unhappy because this is exactly what the rules of the game tell us. Now, of course, I have created this agent, but I haven't actually put it into the model. To put it into the model, we use a function called add_agent. This is a function that comes from Agents.jl and will add an agent into the model. But actually, I will not use this function. I will use another version that is called add_agent_single. So this function takes as a first argument the agent, as a second argument the model. And this function does the following. It adds the agent to the model, but at a random and empty location of the model, so that you have one agent per location. Because also this is what we want according to the selling, right? It says over here, each position can be occupied by at most one agent. So that's exactly what we are going to do. And then we return the model, return model. So I evaluate this function, and when I say model equals initialize, I don't change any of the default keyword arguments. And now if I go to the console and type the model, you see Julia tells us nicely, that's so nice. This model has 320 agents. That's perfect. So that's already step 3 out of the tutorial. We have 3 more to go. And the fourth step is that you have to create your functions that govern the time evolution of the agent-based model. You can provide an agent stepping function that acts on each agent one by one, and or a model stepping function that steps the entire model as a whole. For our selling example, we don't have any need for a model stepping function. So we will only make this agent stepping function. These functions are standard Julia functions. They don't have anything special, but of course they take advantage of the Agents.jl API. So let's make the function that governs the agent step, function agent step, agent comma model. So this is a function that must take as a first argument an agent of the model and a second argument the actual model. And the rules of the game is, well, the first thing the agent has to do, actually the first thing is not even said. We simply say agent.happy and return. This is a Boolean, the Boolean end that is short circuiting. So this, what I wrote over here is the same as typing if agent.happy return end. So this line is equivalent with these 3 lines. And what it does, it simply says, if the agent is happy, do nothing. We don't care. That's it. It stays where it is. And now we start the actual selling process. So the first step is that the agent has to count the agents nearby it that belong to the same group. How do we do this? Well, we first initialize a counter that is C, or let's say nearby same. These are the agents nearby our own agent that are belonging to the same group. And then we can say the following: for neighbor in nearby agents, agent comma model. This is a function from Agents.jl that takes as an input an agent or a location on the space and the model, and then some other optional arguments that we do not care about at the moment. And this function returns to us an iterable that contains all the agents that are nearby. Let me demonstrate in the REPL. I can say agent equals model 42. This gives me the agent that has ID 42 inside the model. Okay? And then I type nearby agents, agent comma model. In fact, I will collect this. I will tell you in a moment why. Sorry. Never code live, right? Nearby agents. So this gives me 6 agents. The reason they are not 8 is because, of course, there could be some locations nearby our agent that are empty. They have no agent, so that's normal. So these are the agents nearby our agent. And as you can see, if I type again agent is at location 2,3 on the grid. So the locations of the agents match. Now, the reason I collected this is because this is a dynamic iterator that iterates dynamically and without allocating memory. So if that means that you cannot display it as a vector, but if you collect it, then it allocates a vector that stores everything. This is some performance optimization. Nevertheless, we are iterating through this vector over here. So these are our neighbors. And then this is a very simple if statement. We say if agent.group is the same as the neighbor.group, well, just increment the counter, the nearby same counter with 1. And that's the end of the story. So now we have counted how many agents are nearby our own agent that belong to the same group. And then a simple if clause decides the remaining of the selling model. So if nearby same is greater or equal than model dot mean to be happy, agent happy equals true. So if we have at least this amount of people nearby that are in the same group, we become happy. But if not, then what do the rules say? If the agent is unhappy, it moves to a new random location. That's very nice and convenient for us because we have a very nice function over here called move agent single agent model that moves the agent to another location on the grid, randomly chosen, but under the requirement that there can be only one agent per grid location. And
Good question.
Yes.
Could you explain again how you did the larger equal sign?
Oh yeah, that is a feature of Julia, my dear friend.
Okay.
And you see, Julia can use any Unicode symbol as you would use in math, like alpha, beta, gamma. You can make them variables. And in every Julia editor that exists, if you press the slash sign and then you type the LaTeX notation for a symbol, and you press tab,
okay.
you get
Nice.
the symbol. So this symbol is fully equivalent with this symbol that you would type in other programming languages, but of course it looks much, much better. So that's some really nice fancy stuff from Julia. So let me demonstrate this move agent single function. So remember, our agent is at this location over here. So now I will type move agent single agent model. And you see that our agent has moved to another location that is 6,12. So that does what we expect, or at least you should trust me that it does what we expect. And then we simply finish the function. And that's the end of the story. Now that we have this function, the only thing we have to do is call the function step, model, and then agent step. This function will take the model and these rules for the model evolution and progress it for one step. This means it will schedule all the agents and then loop through the agents and apply this function to them, right? And furthermore, you could also type it like this: step model, comma, agent step, step, comma 3. This means that it will step the model for 3 steps. And there is another option. Let me copy this one. And the other option is this one, done step, comma 3. Remember when I told you that you can provide 2 stepping functions, one for the agents and one for the model. Now this variable, the third variable in this kind of syntax, would be the stepping function for the model. In our case, the model does not have any dynamics, so we use the predefined dummy step function that, as you would expect, does absolutely nothing. Now, you would care about this syntax because you might have model stepping properties, but also another way to step the model is to define your own function for when the model will terminate. So let me give you an example. I define a function called T for terminate, and this function must take 2 arguments. The first argument is the model, and the second argument is S. S will be the current step counter during the model evolution. When this function returns true, model evolution stops. So you could do some fancy stuff with model here, but I'm not going to do that. I will simply say S equals 3. All right. So now this means, let me reinitialize the model from 0 and then copy this and give here T. So what these 3 lines will do, if I evaluate them, they will step the model until the step number is 3. So it's equivalent with the above, of course, but I'm letting you know that here you could write anything you can possibly imagine, any function of the model, as long as it returns true, it would terminate the time evolution. Perfect. So this is already step 4 done. So we are back to the tutorial. Step 5 is the optional step, which is, in my opinion, the coolest step, which is to visualize the model and animate its time evolution. And to do this, you have to load 2 packages. The first is Interactive Dynamics. This is a Julia package that provides visualization functionality for many packages of the Julia Dynamics organization, one of which is Agents.jl. The second package is GLMakia, which is a very, very good Julia plotting library. So I've loaded these packages over here. Now, to plot a model, I can simply call ABM plot model. We, of course, wait a bit. So let me try to find now where this window is. Sorry, my mistake. I will never find this window because I have to type this command. I forgot about this. By default, this creates a plot but does not display it, which is the typical way people work with plots in Julia. But if you want to display it, you call display on the return figure. Sorry, I meant display. And now the figure exists. You don't see it because it's in my other screen, but I promise you will see it in a moment. Let me bring it over here. Wait, sorry. Not easy. All right, so this is the plot. And I will also pin it over here. So this nice plot plots the ABM. Unfortunately, this is not very interesting because all agents are plotted with the default arguments, which is purple color and circle as a market. But changing this is trivial, trust me. To change the way agents are plotted, you simply create a function that decides what is the color of the agent, a function that decides what is the marker, a function that decides what is the size. For example, I will create a function called group color, and this function takes as an input an agent. And this function says, if agent group is equal to 1, then return color blue. Otherwise, return color orange. So that this function will decide the color of each individual agent. And then I create another function that is group marker. And this function will decide the marker of the agent. And this will be circle for group 1 and just a rectangle for group 2. All right. Now, I copy paste this, and I only have to give these functions as arguments to the ABM plot function. So the argument AC stands for agent color, and it takes the group color function. And the argument AM starts for agent marker, and it takes the group marker function. Now, when I do this and I evaluate these lines again, and now the plot is recreated, and now you see the agents of group 1 are blue with circles, and the group 2 are orange rectangles. That's how plotting works with agents. It's really is straightforward. But if you want to animate this model, well, you could simply export it into a video, but we have an application that shows the real-time evolution of the model. So let me restart the model. Model is equals initialize model. That's very nice. How are we doing on time? What time did we start?
Oh, I think, we are flexible because, we have time to so, just I think you don't need to rush. At least for me, how fast you go is very good.
yeah, but you are an expert, my friend. So I'm probably going fast, but it's okay. Yes, equals, let's make it 12. Okay, now instead of ABM plot, I now use a different function called ABM play. This function takes the model, but also the stepping functions, right? Notice the ABM plot does not take any stepping functions because, well, it doesn't step the model. This function will step the model. And of course, I also give the nice plotting keyword arguments. And here I also adjust the agent size, but I don't bother to give it a function for each individual agent. I just say all agents have size 12. All right, so now I will evaluate this again. And now you see, I have the same plot as before, but now I have some fancy sliders over here. I have a button step that once I press it, it steps the model for one step. It presses one step. Now, unfortunately, the model already converged to equilibrium after 5 steps, but I can thankfully reset. And now I can click run, and the model will run, having 1 second per step. And the model, as I can see, has already converged. I reset it again. I can also change the speed that the model is evolved by changing the speed slider. Unfortunately, if I make this too small, it will be a bit useless because it will evaluate instantly. So I cannot go all the way to 0 because the model will run instantaneously. So this, as I hope you can already understand, this way of visualization and plotting and animating is generic. It doesn't matter what kind of model I have, what are its stepping properties, and also, in fact, it doesn't matter if I have a grid space or continuous space. Exactly the same commands, exactly the same 3 lines of code will do exactly the same thing for your own model. So plotting with agents is really, 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 really simple. It only takes you 3 lines of code. And you have full flexibility over these properties. You could, in fact, make each single agent a different marker, and probably not very useful, but you could do it. All right. I mean, it's going great. We are now actually in the very final step of this tutorial, so to speak, which is collect data. Of course, if you're doing agent-based modeling for scientific purposes, you typically want to collect data from your simulation and actually analyze this data. So here is the last step, step 6, collect data. How do you do this? Well, the first part, if I go back to the tutorial, it says, the first part is to specify which data should be collected by providing one standard Julia vector of data to collect for the agents. And you could also do one for the model, but our model doesn't have much useful data at the moment. So I say add data, which is agents data, equals what would be group, and happy. So this simply tells us which properties of the agents do you want to collect as data, all right? Now, this vector exists in memory, that's nice. And then the only thing I have to do is agent data frame, nothing, equals, I have to call the run function, right? The run function takes the same arguments as the step function. Let me copy paste this over here so that you see the similarities. So the run function takes the same arguments as the step function. So model agent step. As we said, there is no dynamics for the model stepping part. So we can put dummy step. We don't care about this. And then let's step it for three steps. Now the first arguments are the same. And then we go into the keywords. The run function also takes keywords because it steps the model and collects data at the same time. So the keyword a data that we already have evaluated will tell the function what data to collect. Now the function returns 2 arguments. The first is the data frame that has the agent collected data, and the second is the model data frame that has the model collected data. And as you can see here, I actually don't put it into any variable because it's empty and I will not use it. So I run this very nice piece of code, and this has evaluated. So let's see what is ADF. I come here and I type ADF. ADF is a data frame, and it has here 4 columns. This is the step number, and by default, it always collects data before stepping the model. The second column is the ID number, the ID, which is the unique agent identifier. The third column is the Boolean, the group, and the last column is whether the agent is happy or not, right? So let me model equals initialize. Let me run it again so that you can see that, in fact, the agents start unhappy, and by the end, some of them are happy, okay? Besides this, that is a bit restrictive because you can only collect data that agents have explicitly as their property. Well, that's not true. You can actually collect whatever you can possibly imagine because we allow you to define any function that you want that takes as an input an agent and outputs anything. And you can collect data according to this function. So here I create a function called X that takes as an input an agent and returns the agent's X coordinate. So you see I access the position of the agent and I get the first argument, which is the X coordinate. Then I simply modify this add data variable to have one more function, one more argument that is X. And notice X is a function, right? It's not a name or anything, it's just a function. So let me run this thing again. I think I made a silly mistake somewhere. Damn it, never code live. Agents not defined. Of course. Yeah, never ever code live, truthfully. So now I run again the model called data collection, and I have this very nice vector. And if I go to the collected data frame, we see that it has one additional column now, that is this X. And it is, of course, the first coordinate of the agent. So that's how things work. But of course, typically or often, you don't want to collect data for each individual agent, especially when you have very large models, because then the amount of data you collect will explode. That's why we have an aggregating option. Instead of collecting data for each agent, you can in fact aggregate over all agents and present an averaged or aggregated property when you collect the data. How do you do this? Well, you modify this vector over here. We don't need group anymore. You modify this vector as follows. Now, instead of having individual entries, each entry of this vector will be a tuple, okay? So a tuple where the first element of the tuple will be the data I want to collect. So here, this is the happy property. The second entry of the tuple will be the function that will aggregate this property. For the happiness, I use the sum function. So this will simply count or sum up how many agents are happy, okay? And for the X property, I will use the mean function. So this function will average all of these X coordinates. Actually, using statistics mean, I have to bring the mean function into scope because by default, it's not in scope in Julia. So now I have modified the data collection vector, and I copy paste the same thing over here. I once again create a model from 0 and I put it into the data collection, but now with this vector. So let's see what the data frame is now. And you see now the data frame is wildly different. There is no column ID because I have aggregated over the agents. And instead there is the sum happy property, which is how many agents are happy. Before the model starts checking, they are 0 because they all start unhappy. And over time, more and more become happy. Now, X is the average of the agent's X coordinate. And as you can see, is about 10.5, as it should be, because that's the average coordinate of the grid and agents are distributed randomly. So that's how things work. And I think I will stop here actually and go into the exercises because, yeah, in case you didn't know, the remaining of this workshop is that you guys try and do some exercises, which is extremely important. You cannot learn agents by listening to me talk. You have to do it yourselves. So I'm going back to the slides. And where are the slides? Just give me 1 second. Nothing is easy in the COVID era. Yep, here we are.